Sleep and study. Don't forget to subscribe.
We're going to move now into actually solving the Schrödinger equation. This is really the main meat of quantum mechanics. And in order to start tackling the Schrödinger equation, we need to know a little bit about how equations like the Schrödinger equation are solved in general. One of those solution techniques is separation of variables, and that's the solution technique that we're going to be applying repeatedly to the Schrödinger equation. First of all, though, let's talk a little bit about ordinary and partial differential equations. The Schrödinger equation is a partial differential equation, which means it's a good deal more difficult than an ordinary differential equation. But what does that actually mean? First of all, let's talk about ordinary differential equations. What an ordinary differential equation tells you is how specific coordinates change with time. At least that's most applications. So you have something like x as a function of time, y as a function of time, sorry, not y as a function of x, y as a function of time, z as a function of time. For example, the position of a projectile moving through the air could be determined by three functions, x, y, and z. If you're only working in two dimensions, for instance, let me drop the z, but we might have a velocity as well, say vx of t and vy of t. These four coordinates, position in two dimensions and velocity in two dimensions, fully specifies the state of a projectile moving in two dimensions. What an ordinary differential equation might look like to govern the motion of this projectile would be something like the following. dx dt is vx, dy dt is vy. Nothing terribly shocking there. The position coordinates change at a rate of change given by the velocity. Well, the velocities change, dvx dt, is given by, let's say, minus kvx, and dvy dt is minus kv subscript y now, kvy minus g. This tells you that where I got these equations, this is effectively damped frictional motion in the plane xy, where gravity is pulling you down. So in the absence of any velocity, gravity leads to an acceleration in the negative y direction, and the rest of this system evolves accordingly. What that tells you, though, in the end, is the trajectory of the particle. If you launch it as a function of time, tick, 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 as the projectile moves through the air in, say, x, y space. Partial differential equations, on the other hand, PDEs, you have several independent variables. So where in an ordinary differential equation we only had time, and everything was a function of time, in a partial differential equation, what you're trying to solve for will have several independent variables. For example, the electric field, the vector electric field in particular, as a function of x, y, and z. The electric field has a value, both a magnitude and a direction, at every point in space, so x, y, and z potentially vary over the entire universe. Now you know how, excuse me, you know a few equations that pertain to the electric field that maybe you could use to solve to determine what the electric field is. One of these is Gauss's law, which we usually give an integral form. The integral of the electric field dotted with an area vector over a closed surface is equal to the charge enclosed by that surface over epsilon naught. Now hopefully you also know there is a differential form for Gauss's law, and it usually is written like this. This upside down delta is read as del, so you could say this is del dot E, and this is a vector differential operator. I'm going to skip the details of this because this is all electromagnetism, and if you go on to take advanced electromagnetism courses, you will learn about this in excruciating detail. Perhaps suffice to say here that most of the time when we're trying to solve equations like this, we don't work with the electric field, we work with the potential, let's call that V, and this system of equations here, if you treat the electric field as minus the gradient of the potential gives you this equation gives you the Laplace equation. Del squared V equals rho over epsilon naught. What that actually writes out to, if you go through all of the vector algebra, is the second derivative of v with respect to x plus the second derivative of v with respect to y plus the second derivative of v with respect to z, and I've left off all my squareds in the denominator here, is equal to rho over epsilon naught. This is a partial differential equation, and if we had some machinery for solving partial differential equations, we would be able to determine the potential at every point in space. And that would then allow us to determine the electric field at every point in space. This is just an example. Hopefully you're familiar with some of the terms I'm using here. The main solution technique that is used for partial differential equations is separation of variables. And separation of variables is fundamentally a guess. Suppose we want to find some function. In the case of electromagnetism, it's the potential x, y, and z. The potential is a function of x, y, and z. Let's make a guess that v of x, y, and z can be written as x of x times y of y times z of z. So instead of having one function of three variables, we have the product of three functions of one variable each. Does this guess work? Well, it's astonishing how often this guess actually does work. This is a very restrictive sort of thing, but under many realistic circumstances, this actually tells you a lot about the solution. For example, the wave equation. The wave equation is what you get mathematically if you think about, say, having a string stretched between two solid objects. Now, under those circumstances, if you zoom in on, if you say, pluck the string, you know it's going to vibrate up and down. Mathematically speaking, if you zoom in on a portion of that string, say it looks like this, you know the center of this string is going to be accelerating downwards. And the reason it's going to accelerate downwards is because there is tension in the string, and the tension force pulls that direction on that side and that direction on that side. So it's being pulled to the right and pulled to the left, and the net force then ends up being in the downward direction. If the string curved the other direction, you would have effectively a net force pulling up and to the right, and a net force pulling up into, or a force pulling up into the right, a force pulling up into the left, and your net force would be up. This tells you about forces in terms of curvatures, and that thought leads directly to the wave equation. The acceleration, as a result of the force, is related to the curvature of the string. And how we express that mathematically is with derivatives. The acceleration is the second derivative of the position. So if we have the position of this string is u as a function of position and time, then the acceleration of the string at a given point and at a given time is going to be equal to some constant, traditionally written c squared, times the curvature, which is the second derivative of u with respect to x. Again, u being a function of position and time. So this is the wave equation. I should probably put a box around this because the wave equation shows up a lot in physics. This is an important one to know. But let's proceed with separation of variables. U, as a function of position and time, is going to be x, a function of, not time, x a function of position, and t a function of time. So capital X and capital T are functions of a single variable each, and their product is what we're guessing will reproduce the behavior of u. So if I substitute this u into this equation, what I end up with is the second derivative of x, t of t, with respect to time, equals c squared times the second derivative of x, t of t, with respect to position. So this hasn't really gotten us anywhere yet, but what you notice here is we have derivatives with respect to time, and then we have this function of position. Since these are partial derivatives, they're derivatives taken with everything else other than the variable that you're concerned with held constant, which means this part here, which is only a function of position, can be treated as a constant and taken outside of the derivative. The same sort of thing happens here. We have second derivatives, partial second derivatives with respect to position, and here we have only a function of time, effectively a constant for this partial derivative, which means we can pull things out. And what we've got then is capital X. I'm going to drop the parentheses x because you know capital X is a function of lowercase x. So you've got big X, second partial derivative with respect to time of big T equals c squared big T, second partial derivative of big X with respect to x. That's nice because you can see we're starting to actually be able to pull x and t out here. And the next step is to divide both sides of this equation by xt, by basically dividing through by u. In order for this to work, we need to know that our solution is non-trivial, meaning if x and t are everywhere 0, dividing through by this will do bad things to this equation. But what you're left with after you divide by this is 1 over t, second partial of t, big T with respect to little t, and c squared 1 over big X, second partial of big X with respect to little x. This is fully separated. What that means is that the left-hand side here is a function only of t. And the right-hand side is a function only of x. That's very interesting. Suppose I write this function of t as, say, f of t. This part, let's call that g of x. I have two different functions of t and x. Normally you would say, oh, I have f of t and I have g of x, and I know what those forms are. I could, in principle, solve for t as a function of x. But that isn't what you're going to do, and the reason that's not the case is that this is a partial differential equation. Both x and t are independent variables. All of this analysis, in order for separation of variables to work, must hold at every point in space, at every x and at every time. So suppose this relationship held for a certain value of t and for a certain value of x. I ought to be able to change x and have the relationship still hold. So if I change x without changing t, the left-hand side of the equation isn't changing. If changing x led to a change in g of x, then my relationship wouldn't hold anymore. So effectively what this means is that g of x is a constant. In order for this relationship to hold, both f of t and g of x have to be constant. Essentially, what this is saying in the context of the partial differential equation is that if we look at the x part here, when I change the position, any change in the second derivative of the position function is mimicked by this 1 over x, such that the overall function ends up being a constant. That's nice, because that means I actually have two separate equations. F of t is a constant and g of x is a constant. What these equations actually look like. This was my f of x, and this was my f of t, and this was my g of x. That constant, which I've called a here, and the notation is arbitrary, though you can in principle save yourself some time by thinking ahead and figuring out what might be a reasonable value for a. What's especially nice about these is that this equation is now only an ordinary differential equation. Since big T is only a function of little t, we just have a function of a single variable. We only have a single variable here. We don't need to worry about what variables are being held constant and what variables aren't being held constant. So we can write this as total derivative with d instead of partial derivative with the partial derivative symbol. So we've reduced our partial differential equation into two ordinary differential equations. This is wonderful. And we can rearrange these things to make them a little more recognizable. You've got d squared t dt squared equals a t, and c squared d squared big X d little x squared equals a times big X, multiplying through by big T in this equation and big X in this equation. And these are equations that you should know how to solve. If not, you can go back to your ordinary differential equations books, and solution to ordinary differential equations like this are very commonly studied. In this case, we're taking the second derivative of something and we're getting the something back with a constant out front. Anytime you take the derivative of something and get itself, or itself times a constant, you should think exponentials. And in this case, the solution is t equals e to the square root of a times time. If you take the second derivative of this, you'll get two square roots of a factors that come down, e times e to the root at, which is just big T. You can, in principle, also have a normalization constant out front, and you end up with the same sort of thing for x. Big X is going to be e to the square root of a over c x, with, again, in principle, a normalization constant out front. What that means is, if I move things up a little bit, get myself some space, u of x and t, what we originally wanted to find, is now going to be the product of these two functions. So I have a normalization constant in front, then I have e times root a t, and e times root a over c x. Now, if this doesn't look like a wave, and that surprises you because I told you this was the wave equation, it's because we have, in principle, some freedom for what we want to choose for our normalization constant and for what we want to choose for our separation constant, this constant a. And the value of that constant will, in principle, be determined by the boundary conditions. A and a are determined by boundary conditions. The consideration of boundary conditions and initial conditions in partial differential equations is subtle, and I don't have a lot of time to fully explain it here. But if what you're concerned with is why this doesn't look like a wave equation, what actually happens when you plug in to your initial conditions and your boundary conditions to find your normalization constants and your actual value for the separation constant, you'll find that a is complex. And when you substitute in the complex value for a into these expressions, you'll end up with e to the I omega t sort of behavior, which is going to give you effectively cosine of omega t, up to some phase shifts as determined by your normalization constant and your initial conditions. So this is how we actually solve a partial differential equation. The wave equation in particular separates easily into these two ordinary differential equations, which have solutions that you can go and look up pretty much anywhere you want. Finding the actual value of the constants that match this general solution to the specific circumstances you're concerned with can be a little tricky, but in the case of the wave equation, if what you want is, say, a traveling wave solution, you can find it. There are appropriate constants that produce traveling waves in this expression. So, to check your understanding, what I'd like you to do is go through that exercise again, performing separation of variables to convert this equation into, again, two ordinary differential equations. This equation is called the heat equation, and it's related to the diffusion of heat throughout a material. If you have, say, a hot spot and you want to know how that hot spot will spread out with time. Since this is a quantum mechanics course, let's move on to the time-dependent Schrodinger equation. This is the full Schrodinger equation in all of its glory, except I've just written it in terms of the Hamiltonian operator now. H hat is the Hamiltonian. The Hamiltonian is related to the total energy. I evidently can't spell total energy of the system, meaning it's, kinetic energy plus potential. And we have a kinetic energy operator, and we have, well, we will soon have a potential energy operator. What h hat actually looks like is it's the kinetic energy operator, which, if you recall correctly, is minus h bar squared over 2m times the second derivative with respect to position. And the potential energy operator is just it looks a lot like the position operator. It's just multiplying by some potential function, which here I'll consider to be a function of x. Now this is an operator, which means it acts on something, so I need to substitute in a wave function here. And when you do that in the context of the Schrodinger equation, you end up with the form that we've seen before. I h bar d psi dt equals minus h bar squared over 2m d squared psi dx squared plus v of x psi. So that's our Schrodinger equation. How can we apply separation of variables to this? Well, we make the same sort of guess as we made before. Namely, psi is going to be xt, where big X is a function of position and big T is a function of time. If I substitute psi equals xt into this equation, you get pretty much what you would expect. I h bar. Now when I substitute xt in here, big X, big T, big X is a function only of position, so I don't need to worry about the time derivative acting on big X. So I can pull big X out, and what I'm left with then is a time derivative of big T. This is then going to be equal to minus h bar squared over 2m times the same thing. When I substitute xt in here, the second derivative with respect to position is not going to act on the time part, so I can pull the time part out. T, second derivative of big X with respect to position. And substituting an xt here doesn't really do anything. There's no derivatives here, so this is not a particularly interesting term. So we're getting vxt. All right. Now the next step in separation of variables is to divide through by your solution, xt, assuming it's not 0, that's okay. And you end up with I h bar 1 over big T, canceling out the x, and you're just left with big T. 1 over t, partial of t dt. And then on the right-hand side, we have minus h bar over 2m, h bar squared over 2m, 1 over big X, second partial of x with respect to position, plus v. X and t are fully canceled out in this term. Now, as before, this is a function of time only, and this is a function of space only, which means both of these functions have to be constant. And in this case, the constant we're going to use is E. And you'll see why once we get into talking about the energy in the context of the wave function. So we have our two equations. One, I h bar over t, first partial derivative of big T with respect to time, is equal to E. And on the right-hand side, from the right-hand side, we get minus h bar squared over 2m, 1 over big X, second partial of big X with respect to position, plus V is equal to the energy. So these are our two equations. Now I've written these with partial derivatives, but since, as I said before, these functions big T and big X are only functions of a single variable, there's effectively no reason to use partial derivative symbols. I could use d's instead of partials. Essentially, there's no difference if you only have a function of a single variable, whether you take the partial derivative or the total derivative. So, let's take these equations one by one. The first one, the time part. This we can simplify by multiplying through by big T, as before, and you end up with I h bar d big T dt equals e times t. Taking the derivative of something and getting it back multiplied by a constant, again, should suggest two exponentials. Let me move this IH bar to the other side. So we would have divided by IH bar. And 1 divided by I is minus I. So I'm going to erase this from here and say minus I in the numerator. So first derivative with respect to time of our function gives us our function back with this out front. Immediately this suggests exponentials, and indeed our general solution to this equation is some normalization constant times e to the minus I e over h bar times time. So if we know what this separation constant capital E is, we know the time part of the evolution of our wave function. This is good. What this tells us is that our time evolution is actually quite simple. It's in principle a complex number. T is, in principle, a complex number. It has constant magnitude. Time evolving this doesn't change the absolute value of capital T. And essentially it's just rotating about the origin in the complex plane. So if this is my complex plane, real axis, imaginary axis, wherever capital T starts, as time evolves, it just rotates around and around and around and around in the complex plane. So the time evolution that we'll be working with, for the most part, in quantum mechanics is quite simple. The space part of this equation is a little more complicated. All I'm going to be able to do now is rearrange it a little bit by multiplying through by capital X, just to get things on top, and change the order of terms a little bit to make it a little more recognizable. Minus h bar squared over 2m, second derivative of capital X with respect to position, plus v times capital X is equal to e times capital X. And this is all the better we can do. We can't solve this equation because we don't know what v is yet. V is where the physics enters this equation and where the wave function from one scenario differs from the wave function for another scenario. Essentially, the potential is where you encode the environment into the Schrödinger equation. Now, if you remember back a ways, when we were talking about the Schrödinger equation on the very first slide of this lecture, what we had was the Hamiltonian operator acting on the wave function. And this is that same Hamiltonian. This is h hat, not acting on psi now, just acting on x. So you can also express the Schrödinger equation as h times x equals e times x. The Hamiltonian operator acting on your spatial part is the energy of, is the separation constant E, which is related to the energy, times the spatial part. So this is another expression of the Schrödinger equation. This equation itself is called the time-independent Schrödinger equation, or TISE if I ever use that abbreviation. And this is really the hard part of any quantum mechanics problem. To summarize what we've said so far, starting with the Schrödinger equation, which is this: time derivatives with complex parts in terms of Hamiltonians and wave functions gives you this, substituting in the actual definition of the Hamiltonian, including a potential v. And applying separation of variables gets us this pair of ordinary differential equations. The time part here gave us numbers that just basically spun around in the complex plane. Not the imaginary part. This is traditionally the real part, and this is the imaginary part. So the time evolution is basically rotation in the complex plane. And the spatial part, well, we have to solve this equation being the time-independent Schrödinger equation. We have to solve this for a given potential. The last comment I want to make in this lecture is a comment about notation. My notation is admittedly sloppy, and if you read through the chapter, Griffiths calls my notation sloppy. In Griffiths' since it has the luxury of being a book and not the handicap of having my messy handwriting, they use capital psi to denote the function of x and time. And when they do separation of variables, they re-express this as lowercase psi as a function of position and lowercase phi as a function of time. So for this, I used capital X. Sorry, I should put things in the same order. I used capital T of t and capital X of x, because I have a better time distinguishing my capital letters from my lowercase letters than trying to, well, you saw how long it took me to write that symbol. I'm not very good at writing capital psis. There is a lot of sloppiness in the notation in quantum mechanics, namely because, oops, geez, I have two functions of time. This is Griffith's function of position. Sorry about that. This here and this here, these are really the interesting parts, the functions of position, the solutions to the time-independent Schrödinger equation. What that gives us, well, what that means is that a lot of people are sloppy with what they call the wave function. This is the wave function. This is the spatial part, or the solution to the time-independent Schrödinger equation. This is not the wave function. But, I mean, I've already made this sloppy mistake a couple of times in problems that I've given to you guys in class. Namely, I'll ignore the time domain part and just focus on the spatial part, since that's the only interesting part. So, perhaps that's my mistake. Perhaps I need to relearn my handwriting. But, at any rate, be aware that sometimes I, or perhaps even Griffiths, or whoever you are talking to, will use the term the wave function when they don't actually intend to include the time dependence. And the time dependence is, in some sense, easy to add on because it's just this rotation in complex number space. But hopefully things will be clear from the context what is actually meant by the wave function. So we're still moving toward solutions to the Schrödinger equation. And the topic of this lecture is what you get from separation of variables and the sorts of properties it has. To recap what we talked about last time, the Schrödinger equation, I h bar partial derivative of psi with respect to time is equal to minus h bar squared over 2m second partial derivative of psi with respect to position plus v times psi, where this is essentially the kinetic energy and this is the potential energy as part of the Hamiltonian operator. We were able to make some progress towards solving this equation by writing psi, which is in principle a function of position and time, as some function of position multiplied by some function of time. Why did we do this? Well, it makes things easier. We can make some sort of progress, but haven't we restricted our solution a lot by writing it this way? Well, really we have, but it does make things easier, and it turns out that these solutions that are written as products that result from solving the ordinary differential equations you get from separation of variables with the Schrödinger equation can actually be used to construct everything that you could possibly want to know. So let's take a look at the properties of these separated solutions. First of all, these solutions are called stationary states. What we've got is psi as a function of position and time is equal to some function of position multiplied by some function of time. And I wrote that as capital T on the last slide, but if you remember from the previous lecture, the time evolution equation was solvable, and what it gave us was a simple exponential, e to the, minus I times e times t divided by h bar. So this is our time evolution part, and this is our spatial part. What does it mean for these states to be stationary? Well, consider, for instance, the probability density for the outcome of position measurements. Hopefully you remember this is equal to the squared absolute magnitude of psi, which is equal to the complex conjugate of psi times psi. Now if I plug this in for psi and its complex conjugate, I end up with the complex conjugate of big X as a function of position times the complex conjugate of this. And the only part that's complex about this is the I here in the exponent, so we need to flip the sign on that. And we'll have e to the I, positive I now, e t over h bar. That's for the complex conjugate of psi. And for the psi itself, well, x of x e to the minus I e t over h bar. Now, multiplying these things together, there's nothing special about the multiplication here, and this are complex conjugates of each other, so they multiply together to give the magnitude of the squared magnitude of each of these numbers together, which, since these are just complex exponentials, is magnitude 1. So what we end up with here is x star x, essentially the squared magnitude of just the spatial part of the wave function. There's now no time dependence here, which means the probability density here does not change as time evolves. So that's one interpretation of these, or one meaning of these things being called stationary states. The fact that I can write a wave function as a product like this, and the only time dependence here comes in a simple complex exponential, means that that time dependence drops out when I find the probability distribution. Another interpretation of these things as stationary states comes from considering expectation values. Suppose I want to calculate the expectation value of some generic operator, capital Q. The expression for the expectation of an operator is an integral of the wave function times the operator acting on the wave function. So complex conjugate wave function, operator, wave function. Now I'm going to go straight to the wave function as expressed in terms of x and t parts. So complex conjugate of the spatial part times the complex conjugate of the time part, which from the last slide is e to the plus I e t over h bar. Our operator gets sandwiched in between the complex conjugate of the wave function and the wave function itself. So this is again, no stars anymore, come on Brett, just x and then e to the minus I e t over h bar. And this is all integrated dx. So this is psi star, and this is psi. And this is our operator sandwiched between them, as in the expression for the expectation. Now, provided this operator does not act on time, it doesn't have anything to do with the time coordinate, and that will be true for basically all of the operators we will encounter in this course, has no time derivatives. What that means is that I can push this time part past the operator. The operator will not act on the time part, so that's okay. And what that means is, as before, these two guys will just end up directly multiplied by each other, excuse me, and you will end up with just 1 as a result. Integral of x star q hat x dx will be what results. Again, the time part drops out if, q has no partial time derivatives, which is true for basically all of the operators we'll meet. Position, x hat, that's just multiplying by x. Momentum, that has to do with differentiation with x. And then kinetic energy, that again has second derivatives with respect to position. There's no time derivatives in any of these physical sorts of operators that we'll be talking about here. What that means is that, again, the time dependence drops out, and the expectation value of this Q operator, and Q can be anything here, again, has no time dependence. So our expectation values are constant. If our physical system is described by a wave function that separates like this, then our expectation values have no time dependence. The next topic I'd like to address is the energy of a stationary state, which also happens to have a very nice expression. The spatial part of the Schrödinger equation that resulted from our separation of variables was something I call the time-independent Schrödinger equation. The time-independent Schrödinger equation, which could be written simply as the Hamiltonian operator acting on the spatial part of the wave function was equal to the separation constant times the spatial part of the wave function. H times x equals e times x, where h is now an operator, so I shouldn't say time. I should say the Hamiltonian operator acting on x is equal to the separation constant e time just multiplied by the spatial part of the wave function. So suppose I want to calculate the expectation of the Hamiltonian operator. Now the Hamiltonian operator, you know, is related to the energy of the system, so if I calculate an expectation here, it should have something to do with the energy of the system. It's not immediately obvious that h acting on the wave function gives you the energy multiplied by the wave function, but calculating an expectation value like this makes the connection much stronger. So let's write out that expression. We have an integral, and then we have the wave function itself, x star e to the I times the energy times the time over h bar times our Hamiltonian, and then the non-complex conjugated wave function itself, e to the minus I e t over h bar, integral dx. Now we know the Hamiltonian operator, that has partial derivatives with respect to x and multiplication by the potential. So again, this operator isn't going to have any time dependence, same as what we reasoned when we were calculating expectation values. These time dependences drop out for the same reason here as they did in the previous slide in general. We're just left then with the integral of x star h hat x integrated dx. But I know this. That's this. So I can make that substitution. Knowing this spatial part of the wave function solves the time-independent Schrödinger equation allows me to simplify this. I just end up with the integral x star e x integrated dx. Now these x's are not coordinates, they're functions of the x-coordinate, just to be clear about my notation. But this e now, that's just a constant. It can be pulled out of the integral entirely, and we're just left with e times the integral of x star x, should make it clear these are capitals, dx. And this, if we've properly normalized our wave function, is 1. So what that tells us is that the expectation of the Hamiltonian operator is our separation constant, e, that we got when we applied separation of variables to the time-dependent Schrödinger equation. The Hamiltonian operator is something we expect to be related to the energy, so it's reasonable to identify the separation constant E with the energy associated with this particular state. So now what this tells us is that the energy of the wave function, the expectation of our Hamiltonian is the energy of the wave function. Now we know there's some uncertainty in quantum mechanics, so is there uncertainty in our energy? If we actually measure the energy of our wave function, do we ever get E, the separation constant? Well, in order to calculate the uncertainty in something, we need to calculate effectively the standard deviation or the variance. Let's write it as the variance, the squared sigma sub E, where E perhaps now refers to the energy. So let me write this as sigma sub h hat. If we want to calculate this, what we have to calculate, well, sigma sub h hat squared, that's equal to the expectation value of h squared minus the expectation value of h quantity squared, the expectation squared. The expectation of the square minus the square of the expectation. Hopefully you remember that back from when we talked about variance. Now, if I write out this expression, now I just calculated this was equal to E. So this term here is just going to give us E squared. This term is going to give us E squared. So that's easy enough. Let's work with this term then, the expectation of the Hamiltonian squared. This is again going to be an integral, and I'll drop the time-dependent parts here. Actually, you know what? I'll drop all of this. We don't need to actually express everything as an integral. You know what's going to happen in this integral. The expectation of any operator is the integral of psi star times the operator times psi, integrated over the domain, in this case x. So if I substitute the Hamiltonian squared into this, in the context of the discussion we've had over the last few minutes about how the time dependence drops out, what we're effectively going to end up with, needing to consider, is this. And this is going to end up looking like h hat squared times just the spatial part, x. Now h hat squared times the spatial part x, well, that's h hat times h hat acting on h hat acting on x. It's the definition of squaring an operator. You just apply the operator twice. Now, as before, I know this. This is E times x, since I know x satisfies the time-independent Schrödinger equation. So this is going to be h acting on E x. There's nothing special about E, it's just a number, so I can pull it out. The Hamiltonian operator won't do anything to that number. And I'll just be left with E and h hat acting on x. Well, again, h hat acting on x, that's E times x. So I'm going to end up with E squared times x. Now back in the integral equation, this E squared, just being a constant, can be pulled out front. And what we would end up with is E squared times the integral of x star x dx. And again, if we've properly normalized this, this will just be 1, and we'll end up with E squared. So, this is interesting. What we got for our expectation of Hamiltonian squared was E squared. So what this tells us is that sigma sub h hat squared, our variance, or our squared uncertainty in the energy of the system, is equal to E squared from this term minus E squared from this term, which is 0. Stationary states like this that solve the time-independent Schrödinger equation have energy given by the separation constant E and no uncertainty in energy. They essentially have exactly E amount of energy. What exactly does that mean? Well, we'll talk about that in a moment. Just to summarize things, for these stationary states, the probability density has no time dependence. The time-dependent part cancels itself out when you're calculating the probability density. Expectation values of any operator that we're going to be concerned with in this class also have no time dependence. And the energy is specified exactly that separation constant E in, for instance, the time-independent Schrödinger equation h hat x equals E x. This is our energy. That's nice, it has some physical significance. But there's not going to be no uncertainty in energy. These states have defined energy and it's exact, which means if we measured the energy of the system, we would always get the same thing. Now just to comment very briefly on what that actually means. What does it mean for a system to have no energy uncertainty? If you remember back when I talked about the difference between quantum physics and classical physics and where the boundary between classical and quantum physics fell, well, I gave you an energy-time uncertainty relation where the uncertainty in the energy and the uncertainty in the time always had to be greater than about h bar over 2. Now, what does that mean if we have no energy uncertainty? Well, delta E is 0. So 0 times something, it has to be greater than h bar. Now, h bar is really small, but h bar is not 0, so there's mathematically some problem here. And what actually happens is that delta T has to be infinity. What does that mean? Why is that a meaningful statement? Well, essentially this delta T here in the energy-time uncertainty relationship tells you about when the state exists. The duration of the process. Essentially, it's the answer to the question, how accurately can you tell me when this state exists? And for something like a stationary state, it always exists. There's no time dependence. You could run the clock backwards, you could run the clock forwards, all the way before the beginning of the universe, technically, since none of that beginning of the universe stuff is covered in this course. Essentially, this state always exists. So the answer to the question when, well, always, whenever you want, forever, however you want to put it. Essentially, these stationary states always exist. They have no time dependence, and they're constant forever. Now, that's not the most realistic state in the world, but they are the sorts of things that we get from the Schrödinger equation, and they actually have some really, really nice mathematical properties that we'll start talking about in the next lecture and in the lectures after that. But that's a stationary state for you. It's a result of the solution to the time-independent Schrödinger equation, possibly with the time independence added back on, depending on how sloppy I'm being with my notation at any given moment. Stationary states are really important, and they have some very nice mathematical properties. To preview a little bit, if you know the stationary states of your system, you know everything about the system, and you can find the answer to any question you might possibly ask about the quantum mechanical behavior of your system. Now, we talked about how the Schrödinger equation can be split by separation of variables into a time-independent Schrödinger equation and a relatively simple time-dependent part. What that gave us is, provided we have solutions to that time-independent Schrödinger equation, we have something called a stationary state. And it's called a stationary state because nothing ever changes. The probability densities are constant, the expectation values are constant in the state effectively, since it has a precise, exact, no uncertainty energy, has to live for an infinite amount of time. That doesn't sound particularly useful. From the perspective of physics, we're often interested in how things interact and how things change with time. So how do we get things that actually change with time in a non-trivial way? Well, it turns out that these stationary states, while their time dependence is trivial, the interaction of their time dependence when added together in a superposition is not trivial. And that's where the interesting time dynamics of quantum mechanics comes from. Superpositions of stationary states. Now, we can make superpositions of stationary states because of one fundamental fact, and that fact is the linearity of the Schrödinger equation. So the Schrödinger equation, as you hopefully remember it by now, is I, h bar, partial derivative of psi with respect to time, is equal to minus h bar squared over 2m, second derivative of psi with respect to x, and that's a really ugly psi. Must fix. Second derivative of psi with respect to position, plus v times psi. So this is our Hamiltonian operator applied to the wave function, and this is our time dependence part. Now, in order for an equation to be linear, what that means is that if psi solves the equation, psi plus some other psi that also solves the equation will solve the equation. So if, say, let's call it A, solves the Schrödinger equation, and B solves the Schrödinger equation. And let me write this out in a little more detail. First of all, I'm talking about A is a function of position and time, as is B. If A and B both solve the Schrödinger equation, then A plus B must also solve the Schrödinger equation. And we can see that pretty easily. Let's substitute psi equals A plus B into this equation. The first step, I h bar, partial derivative with respect to time of A plus B, is equal to minus h bar squared over 2m, second partial derivative with respect to space of A plus B, plus the potential V times A plus B. Now, the partial derivative of the sum is the sum of the partial derivatives. That goes for the second partial derivative as well. And, well, this is just the product of the potential with the sum is the sum of the product of the potential with whatever you're multiplying out. I'm going to squeeze things a little bit more here. So I can write that out. I h bar d by dt of A plus I h bar dB dt equals minus h bar squared over 2m, second derivative of A, with respect to space, forgot my squared on the second derivative, minus h bar squared over 2m, second derivative of B, with respect to position, plus V times A plus V times B. That's just following those fundamental rules. Now, you can probably see where this is going. This, and this. These three terms together make up the Schrödinger equation, the time-dependent Schrödinger equation for A. For A. For A. And this, and this altogether, that's the time-dependent Schrödinger equation for B. So if A satisfies the time-dependent Schrödinger equation, which is what we supposed when we got started here, then this term, and this term will cancel out. They will obey the equality. Likewise, for the parts with B in them. So essentially, if A solves the Schrödinger equation and B solves the Schrödinger equation, A plus B also solves the Schrödinger equation. And the reason for that is the partial derivatives here. The partial derivative of the sum is the sum of the partials, and the product with the sum is the sum with the products. These are linear operations, so we have a linear partial differential equation, and the linearity of the partial differential equation means, well, essentially that if A solves and B solves, then A plus B will also solve it. That allows us to construct solutions that are surprisingly complicated. And actually, the general solution to the Schrödinger equation is psi of position and time is equal to the sum, and I'm going to be vague about the sum here. You're summing over some index j, x sub j, as a function of position. These are solutions now to the time-independent Schrödinger equation, the spatial part of the Schrödinger equation, times your time part. And we know the time part from the, well, back from when we discussed separation of variables, is minus I e, and now this is going to be e sub j, t, over h bar. So this is a general expression that says we're summing up a whole bunch of stationary state solutions to the time-independent Schrödinger equation. And we're getting psi. Oh, I've left something out, and what I've left out is quite important here. We need some constant, c sub j, that tells us how much of each of these stationary states to add in. So this is actually, well, it's going to be a solution to the Schrödinger equation since it's constructed from solutions to the Schrödinger equation. And this is completely general. That's a little surprising. What that means is that this can be used to express not just a subset of solutions to the Schrödinger equation, but all possible solutions to the Schrödinger equation. All the solutions to the Schrödinger equation can be written like this. That's a remarkable fact. And it's certainly not guaranteed. You can't just write down any old partial differential equation, apply separation of variables, and expect the solutions that you get to be completely general and superposable to make any solution you could possibly want. The reason this works for the Schrödinger equation is because the Schrödinger equation is, well, just to drop some mathematical terms if you're interested in looking up information later on, the Schrödinger equation is an instance of what's called a Sturm-Liouville problem. Sturm-Liouville problems are a class of linear operator equations, for instance, partial differential equations or ordinary differential equations, that have a lot of really nice properties. And this is one of them. So the fact that the Schrodinger equation is a Sturm-Liouville equation, or the fact that the time-independent Schrodinger equation is a Sturm-Liouville equation, means that this will work. So if you go on to study, advanced mathematical analysis methods in physics, you'll learn about this. But for now, you just need to sort of take it on faith that general solutions to the Schrodinger equation look like this: superpositions of stationary states. So if we can superpose stationary states, what does that actually get us? One example I would like to do here is, and this is just an example of the sorts of analysis you can do given superpositions of stationary states, is to consider the energy. Suppose I have two solutions to the time-independent Schrodinger equation, which I'm just going to write as h hat x1 equals e1 x1, and h hat x2 equals e2 x2. So x1 and x2 are solutions to the time-independent Schrodinger equation, and they're distinct solutions. e1 not equal to e2. I'm going to use these to construct a wave function, let's say psi, of x, and at time t equals 0, let's say it looks like this: c1 times x1 as a function of position, plus c2 x2, which is a function of position. Now, at some time later, we can add on our time dependence factors, knowing what the time dependence factors look like. What that means is that psi of x and some general time, each of these spatial parts needs some time part to be inserted. So, c1, x1, and then e to the minus I e1 t over h bar, plus c2 x2 e to the minus I e2 t over h bar. So these complex exponential time dependences come from the time part from our separation of variables. You can think of them as being here as well, just with time t equals 0, which makes both of these factors to be equal to 1. So if this is our wave function, let's consider the energy. In particular, let's consider the expectation value of the Hamiltonian operator. What does that look like? Well, the expectation value is going to be psi star h hat psi integrated dx, and I can substitute in this expression for psi. So I'm going to get an integral of c1 x1 star, taking complex conjugates, e to the I e1 t over h bar. Now I've got a plus sign because I took the complex conjugate, plus c2 x2 star e to the I e2t over h bar. Again, plus sign here because of taking the complex conjugate. Then your operator, and then just psi itself. So c1 x1 e to the minus I e1 t over h bar, so h bar, plus c2 x2 e to the minus I e2 t over h bar. This is all integrated dx. Now, I know what the Hamiltonian does to these time dependence parts, nothing. And I know what the Hamiltonian does to these spatial parts, since, by construction, they're solutions to the time-independent Schrodinger equation. So I can apply the operator to this expression for the wave function. And when you do that, you get c1 x, should be writing my x's bigger here, c1 x1 star e to the I e1 t over h bar. I'm just copying this expression over, plus c2 x2 star e to the I e2 t over h bar. And now after I've applied the operator to this, I get c1 e1 x1 e to the minus I e1 t over h bar. And this is just substituting e1 x1 for h hat x1, plus the same sort of term for the second part, c2 e2 x2 e to the minus I e2t over h bar. Still integrated dx. Now, what do we actually get here? Well, as before, some of these terms are simpler than others. These two terms, when we expand out, distribute this expression, will end up with positive and negative e to the I e1t, e to the minus I e1t multiplied together is going to give us 1. The same thing is going to happen for these two terms when I multiply them together. Now I'm also going to have terms where I have, like this term, where I have e2 and e1 together. e2 and e1 mixed together like that. What I actually get is, expanding this out. Forgot what my slide said for a moment there, sorry about that. This term, the time dependence is going to go away. This term, the time dependence is going to go away. But the cross terms here, those two terms, the time dependence is not going to go away because you have e1 mixed with e2 and e2 mixed with e1. So what you get, expanding that out, is, as before, integral and c1 squared x1 star x1 times e1 with no time dependence. That's what you get from the orange terms here. c1 squared x1 star x1, and then the time dependences drop out, and we have the constant e1 also. From the blue terms here, we get c2 squared x2 star x2 e2 for the same sorts of reasons. Now our cross terms, plus c1 c2 x1 star x2, and then we have, in this case, an e2, and we have some time dependence. E to the I e1 minus e2 t over h bar. Our other cross term looks quite similar, plus c1 c2 x2 star x1 e1 e to the I e2 minus e1 t over h bar. And this is all integrated dx, as before. Now, these integrals actually have some nice features. First of all, this first integral here, the first term in this integral, c1, that's a constant, e1, that's a constant, so I can pull those out, and I'm left with the integral of x1 star x1. If x1 is properly normalized, that integral is going to be 1. So we get c1 squared e1 for this first term. The second term here gives us something that looks very similar, c2 squared e2, since the integral of x2 star x2 is unity, provided we properly normalize things. Now, we're actually done. We'll talk more about this in detail later, but the integral of x1 star x2 is actually going to be 0. Everything else here, c1, c2, e2, and this time-dependent part, is a constant when we're considering an integral over x. So we're just going to be left with the integral of x1 star x2 dx. And this is a general feature of Sturm-Liouville problems. When you have distinct solutions like this, x1 and x2, the integral of their product is 0. Likewise, for x2 star x1 dx equals 0. We'll see a specific example of this in the next lectures when we're talking about the particle in a box. This is connected with Fourier analysis and Fourier series, but for now you can think of it just as a quirk of the nice features of equations like the Schrodinger equation, that you get solutions that split up like this, where your cross terms in integrals like this vanish. So essentially what that tells us is that the expectation of the Hamiltonian is C1 squared E1 plus C2 squared E2. The energies of the states multiply together. In order to check your understanding of this, what I'd like to do is have you follow through similar sorts of analysis, given this wave function, write down in your notebook where the time dependence comes in, and write an expression for the probability distribution as a function of time. And what you need to do to really check your understanding is explain in your own words why this has non-trivial time dependence. That's not an easy question, but the non-trivial time dependence comes from the superposition. The question for you is why and how that superposition results in non-trivial time dependence. So, to summarize, classic problems in quantum mechanics, really they all start with some physical system. For instance, a box with a particle inside it. Now, what happens next depends on what exactly this situation is, but typically in quantum mechanics you will write down a potential, V of x, in the case of one-dimensional quantum mechanics. Knowing that potential will allow you to write down the time-independent Schrödinger equation. That was what we got from separation of variables. So, solving the time-independent Schrödinger equation gives you the stationary states, and it also gives you the energies of those stationary states. That's telling you not x of t, it's telling you x of x and e to the minus I e t over h bar. It's telling you what the stationary state looks like. The next step, and we'll talk about this in great detail, is the expression of the initial conditions of the system as a sum of stationary states. Now, you know superpositions are also going to be superpositions of stationary states are also going to be solutions to the Schrödinger equation. So if you can express your initial conditions as a superposition of those stationary states, you're great. You're good. The final step is to add the time dependence to each stationary state. Knowing x of x, this is the time dependence I'm referring to. You need to know the energy, but you got that. Then, basically what you have is that psi of x and t is equal to that sum over j of x sub j, sorry, I've forgotten again my constant out front, c sub j, x sub j of x, e to the minus I e sub j t over h bar. This is your general solution. You've properly chosen your c sub j's such that you solve your initial conditions. You're guaranteed to solve the Schrödinger equation because you're expressing things as a superposition of stationary states. And this general wave function is then something that you can use to answer meaningful physical questions. Quantum mechanics is really all about solving the Schrödinger equation. That's a bit of an oversimplification, though, because if there was only one Schrödinger equation, we could just solve it and be done with it, and that would be it for quantum mechanics. The reason this is difficult is that the Schrödinger equation isn't just the Schrödinger equation. There are many Schrödinger equations. Each physical scenario for which you want to apply quantum mechanics has its own Schrödinger equation. They're all slightly different, and they all require slightly different solution techniques. And the reason there are many different Schrödinger equations is that the situation under which you want to solve the Schrödinger equation enters the Schrödinger equation as a potential function. So let's talk about potential functions and how they influence, well, the physics of quantum mechanics. First of all, where does potential appear in the Schrödinger equation? This is the time-dependent Schrödinger equation, and the right-hand side here, you know, is giving the Hamiltonian operator acting on the wave function. Now, the Hamiltonian is related to the total energy of the system, and you can see that by looking at the parts. This is the kinetic energy, which you can think of as the momentum operator squared over 2m, sort of a quantum mechanical analog of p squared over 2m in classical mechanics. And the second piece here is, in some sense, the potential energy. This V of x is the potential energy as a function of position. as if this were a purely classical system. For instance, if the particle was found at a particular position, what would be its potential energy? That's what this function v of x encodes. Now we know in quantum mechanics we don't have classical particles that can be found at particular positions. Everything is probabilistic and uncertain, but you can see how this is related. This is the time-dependent Schrödinger equation, which is a little bit unnecessarily complicated. Most of the time, we work with the time-independent Schrödinger equation, which looks very similar. Again, we have a left-hand side given by the Hamiltonian. We have a kinetic energy here, and we have a potential energy here. If we're going to solve this time-independent equation, note now that the wave functions here are expressed only as functions of position, not as functions of time. This operator gives you the wave function itself back multiplied by e, which is just a number. This came from the separation of variables. It's just a constant. And we know from considering the expectation value of the Hamiltonian operator, which is related to the energy, for solutions to this time-independent Schrödinger equation, that we know this is essentially the energy of the state. Now, what does it mean here in this context, or in this potential context? Well, you have a potential function of position, and you have psi, the wave function. So this v of x psi of x, if that varies as a function of position, and it will, if the wave function has a large value, a large magnitude in a certain region, and the potential has a large value in a certain region, that means that there is some significant probability the particle will be found in a region with high potential energy. That will tend to make the potential energy of the state higher. Now, if psi is 0 in some region where the potential energy is high, that means the particle will never be found in a region where the potential energy is high. That means the state likely has a lower potential energy. This is all a very sort of heuristic qualitative argument, and we can only really do better once we know what these solutions are and what these actual potential functions look like. What I'd like to do here before we move on is to rearrange this a little bit to show you what effect the potential energy related to the energy and how it's related to the energy of the state, what effect that has on the wave function. And in order to do that, I'm going to multiply through by this h bar squared over 2m and rearrange terms a little bit. What you get when you do that is the second derivative of psi with respect to x. There's my eraser. With respect to x being equal to 2m over h bar squared times v of x minus e psi. So this quantity here relates the second derivative of psi to psi itself. For instance, if the potential is larger than the energy of the state, you'll get one overall sign relating the second derivative in psi, whereas if energy is larger than potential, then you'll end up with a negative quantity here relating the second derivatives of psi with itself. So keep this in the back of your mind, and let's talk about some example potential functions. This is what we're going to be doing, or this is what the textbook does in all of Chapter 2. Write different potential functions and solve the Schrödinger equation. The first example potential we do, and this is section 2.2, is what I like to call the particle in a box. The textbook calls it an infinite square well. The particle in a hard box, for instance, you can think of as a potential function that looks like this. Get myself some coordinate systems here. You have a potential function v of x, oops, turn off my ruler, that looks something like this. This is v of x as a function of x. The potential goes to infinity for x larger than some size. Let's call this, minus a to a. If you're inside minus a to a, you have 0 potential energy. If you're outside of a, you have infinite potential energy. It's a very simple potential function. It's a little bit non-physical, though, because, well, infinite potential energy, what does that really mean? It means it would require infinite energy to force the particle beyond A. If you had some infinitely dense material that just would not tolerate the electron ever being found inside that material, and you made a box out of that material, this is the sort of potential function you would get. Much more realistically, we have the harmonic oscillator potential. The harmonic oscillator potential is the same as what you would get in classical physics. It's a parabola. This is something, proportional to x squared. V of x being proportional to x squared is what I mean. This is what you would get if you had a particle attached to a spring connected to the origin. If you move the particle to the right, you stretch the spring. Put quantum mechanically, if you happen to find the particle at a large displacement from the origin, the spring would be stretched quite a large amount and would have a large amount of potential energy associated with it. From a more physical, down-to-earth sort of perspective, this is what happens when you have any sort of equilibrium position for a particle to be in. The particle is sitting here near the origin where there is a flat potential, but any displacement from the origin makes the potential tend to increase in either direction. This is like an electron in a particle trap, or an atom in a particle trap. Harmonic oscillator potentials show up all over the place, and we'll spend a good amount of time talking about them. The next potential that we consider is the delta function potential. And what that looks like, now I'm going to start at 0 and draw it going negative, but it's effectively an infinitely sharp, infinitely deep version of this particle in a box potential. Instead of going to infinity outside of your realm, it's at 0, and instead of being at 0 inside your realm, it goes to minus infinity there. This now continues downwards. It doesn't bottom out here. The overall behavior will be different now because the particle is no longer disallowed from being outside of the domain. There is no longer an infinite potential energy here. And we'll talk about that as well. These are all sort of weird, non-physical potentials. The particle in a soft box potential is a little bit more physical. If I have my coordinate system here, the particle in a soft box potential looks something like this. To keep things simple, it still changes instantaneously at, say, minus a and a, but the potential energy is no longer infinity. This is, for instance, a box made out of a material that has some pores in it, and the electron, or whatever particle you're considering to be in the box, doesn't like being in those pores. So there's some energy you have to add in order to push the particle in. Once it's in, it doesn't really matter where it is. You've sort of made that energy investment to push the particle into the box. And we'll talk about the quantum mechanical states that are allowed by this potential as well. Finally, we will consider what happens when there's no potential at all. Essentially, your potential function is constant. That actually has some interesting implications for the form of the solutions of the Schrodinger equation. And we'll talk about that in more detail. To map this onto textbook sections, this is section 2.2. The harmonic oscillator is section 2.3. The delta function potential is section 2.5. The particle in a box is section 2.6. Particle in a soft box is 2.6. And particle with no potential, or an overall constant potential everywhere in space, is section 2.4. So these are some example potentials that we'll be talking about in this chapter. What do these potentials actually mean, though? How do they influence the Schrodinger equation and its solutions? Well, the way I wrote the Schrodinger equation a few slides ago, second derivative of psi with respect to x is equal to 2m over h bar squared, just a constant, times v of x minus e psi. This is now the time-independent Schrodinger equation, so we're just talking about functions of position here. And E, keep in mind, is the energy of the state. If we're going to have a solution to the time-independent Schrodinger equation, this E exists, and it's just a number. So what does that actually mean? Let's think about it this way. We have a left-hand side determined by the right-hand side of this equation. And the left-hand side is just the second derivative with respect to position of the wave function. This is related to the curvature of the wave function. I could actually write this as a total derivative, since this is just psi is only a function of position now. So there's no magic going on with this partial derivatives. It's going to behave same as the ordinary derivative that you're used to from calculus class. The second derivative is related to the concavity of a function, whether something's concave up or concave down. So let's think about what this means. If you have a potential V of x that's greater than your energy, if V of x is greater than E, what does that mean? That means V of x minus E is a positive quantity. That means the right-hand side here will have whatever sign psi has. And I'm being a little sloppy since psi here is in general a complex function. But if we consider it to just be, say, positive, which isn't as meaningful for a complex number as it is for a real number, you would have psi of x. If psi of x is positive and this number is positive, then the second derivative is positive. Which means that if if psi is, say, here, psi is positive, when it's multiplied by is positive, then the second derivative is positive. It curves like this. Whereas if psi is down here, psi is negative, this is positive, second derivative of psi is negative. It curves like this. What this means is that psi curves away from our axis, away from this psi equals 0 line. On the other hand, if V of x is less than the energy, this quantity will be negative, and we get the opposite behavior. If psi is up here, positive, it's multiplied by a negative number, and the second derivative is negative, you get something that curves downwards. If psi is on the other side of the axis, it curves upwards. Psi curves toward the axis. So this helps us understand a little bit about the shape of the wave function. For instance, let me do an example here in a little bit more detail. Suppose I have, I'll do it over here, coordinate system. If I have a potential function, let's do the sort of soft particle in a box. I can do better than that. Soft particle in a box. So V of x is constant outside your central region and constant inside your central region and has a step change at the boundaries of your region. Let's think about what our wave function might look like under these circumstances. So we have our boundaries of our region here. The other thing that we need to know to figure out what the wave function might look like is a hypothetical energy. And I'm just going to set an energy here. I'm going to do the interesting case. Let's say this is the energy. And I'm plotting energy on the same axis as the potential, which is fine. This is the energy of the state. This is the potential energy as a function of position, so they have the same units. What this energy hypothetically means is that outside here, the potential energy is greater than the energy of the state, and inside here, the potential energy is less than the energy of the state. So we'll get different signed sort of behaviors, different curvatures of the wave function. So, do my wave function in blue here. If I say, start my wave function, this is all hypothetical now, this may not work. If I start my wave function here, at some point on the positive side of the axis, at the origin, we know the energy of the state is larger than the energy of, or than the potential energy. So this quantity is negative, and psi curves towards the axis. So since psi is positive here, I'm looking at this sort of curvature. So I could draw my wave function out sort of like this. Maybe that's reasonable, maybe that's not. This is obviously not a quantitative calculation. This is just sort of the sort of curvature that you would expect. Now, I only continued these curving lines out to the boundaries, since at the boundaries, things change. Outside our central region here, the potential energy is larger than the energy of the state, and you get curvature away from the axis. What might that look like? Well, something curving away from the axis. It's going to look sort of like that. But where do I start it? Do I start it going like that? Do I start it going like that? What does this actually look like? Well, if you think about this, we can say a little bit more about what happens to our wave function when it passes a boundary like this. And the key fact is that if v of x is finite, then while we might have the second derivative of psi with respect to x being discontinuous, maybe, might not be. In this case, the second derivative of psi is just set by this difference. So when we have a discontinuity in the potential, we have a discontinuity in the second derivative. The first derivative of psi will be continuous. Think about integrating a function that looks like this. I integrate it once, I get something maybe with large positive slope going to slightly smaller positive slope. There will be no discontinuity in the first derivative. What this means for psi is that it's effectively smooth. And that by that I just sort of mean no corners. The first derivative of psi won't ever show a corner like this. It will be something like that, for example. No sharp corners to it. What that means in the context of a boundary like this is that if I have psi going downwards at some angle here, I have to keep that angle as I cross the boundary. Now once I'm on the other side of the boundary here, I have to curve. And I have to curve according to the rules that we had here. So depending on what I actually chose for my initial point here and what the actual value of the energy was and what the actual value of the potential is outside in this region, I may get differing degrees of curvature. I may get something that happens like this, curves up very rapidly, or I may get something that doesn't curve very rapidly at all. Perhaps it's curving upwards very slowly, but it crosses the axis. Now, as it crosses the axis, the sign on psi here changes. The curvature is also determined by psi. As psi gets smaller and smaller, the curvature gets smaller and smaller, the curvature becoming 0 as psi crosses the axis. Then when psi becomes negative, the sign of the curvature changes, so this would start curving the other direction, curving downwards. It turns out that there is actually a state right in the middle, sort of a happy medium state, where psi curves, and just kisses the axis. Comes towards the axis, and when it comes towards the axis and reaches the axis with 0 slope and 0 curvature, it's stuck. It will never leave the axis again. And these are the sorts of states that you might actually associate with probability distributions. You know if psi is blowing up like this, going to positive infinity or to negative infinity, that your wave function will not be normalizable. But the wave function here, denoted by these green curves, has finite area, therefore is sort of normalizable. So these are the sorts of things that the potential function tells you about the wave function. In general, what direction it curves, how much it curves, and how quickly. And of course, doing this quantitatively requires a good deal of mathematics. But I wanted to introduce the math, or before I introduce the math, I wanted to give you some conceptual framework with which to understand what exactly this potential means. If the potential is larger than the energy, you expect things that curve upwards. And when you get things that curve upwards, you'll have, or curve away from the axis, you tend to have things blow up unless they just sort of go down and kiss the axis like this. So there will be a lot of things approaching the axis and never leaving, so that we have normalizable wave functions. On the other hand, if the potential energy is less than the energy of the state, you get things that curve towards. And well, if you have something that curves towards, it tends to do this. Always curving towards, always curving towards, always curving towards the axis. You get these sort of wave-like states. So that's a very hand-waving discussion of the sorts of behavior you get from, in this case, step discontinuous potential. And we'll see the sort of behavior throughout this chapter. To check your understanding, take this step discontinuous potential and tell me which of these hypothetical wave functions is consistent with the Schrodinger equation. Now, I did not actually go through and solve the Schrodinger equation here to make sure these things are quantitatively accurate. They're probably all not quantitatively accurate. What I'm asking you to do here is identify the sort of qualitative behavior of these systems. Is the curvature right? And let's see. Yeah, are the boundary conditions right? In particular, does the wave function behave as you would expect as it passes from the sort of interior region to the exterior region? We've been talking about solving the Schrodinger equation and how the potential function encodes the scenario under which we're solving the Schrodinger equation. The first real example of a solution to the Schrodinger equation and a realistic wave function that we will get comes from this example, the infinite square well, which I like to think of as a particle in a box. The infinite square well is called that because its potential is infinite and, well, square. What the potential ends up looking like is, if I plot this, going from 0 to A, the potential is infinity if you're outside the region between 0 and A, and at 0 if you're in between the region, if you're in between 0 and A. So what does this look like when it comes to the Schrodinger equation? Well, what we'll be working with now is the time-independent Schrodinger equation, the TISE, which reads minus h bar squared over 2m times the second derivative of, sorry, I'm getting ahead of myself, the second derivative of psi with respect to x plus potential as a function of x times psi is equal to the energy of the stationary state that results from the solution of this equation times psi. Now, this equation doesn't quite look right if we're outside the region. Bad things happen. You end up with an infinity here for v of x if x is not between 0 and a. The only way this equation can still make sense under those circumstances is if psi of x is equal to 0, if x is less than 0 or x is greater than a. So outside this region, we already know what our wave function is going to be. It's going to be 0, and that's just a requirement on the basis of infinite potential energy. Can't really exist in the real world. Now, what if we're inside? Then v of x is 0, and we can cancel this entire term out of our equation. What we're left with then is minus h bar squared over 2m, second partial derivative of psi, with respect to x, is equal to e times psi, just dropping that term entirely. So this is the time-independent Schrodinger equation that we want to solve. So how do we solve it? Well, we had minus h bar squared over 2m times the second derivative of psi with respect to x being equal to e times psi. We can simplify that just by rearranging some constants. What we get, minus second derivative of psi with respect to x equal to minus k squared psi. And this is the sort of little trick that people solving differential equations employ all the time. Knowing what the solution is, you can define a constant that makes a little more sense, in this case using a square for k instead of just some constant k. But in this circumstance, k is equal to root 2m times e over h bar. So this is our constant, which you just get from rearranging this equation. This equation you should recognize. This is the equation for a simple harmonic oscillator, a mass on a spring, for instance. Now, as I said before, the partial derivatives here don't really matter. We're only talking about one dimension, and we're talking about the time-independent Schrödinger equation, so the wave function here, psi, is just a function of x, not a function of x in time. So this is the ordinary differential equation that you're familiar with for things like masses on springs. And what you get is oscillation. Psi, as a function of x, is going to be a sine kx plus b cosine kx. And that's a general solution. A and b here are constants, to be determined by the actual scenario under which you're trying to solve this equation. This equation now, not the original Schrödinger equation. So these are our solutions. Sines and cosines. Sines and cosines. That's all well and good, but that doesn't actually tell us what the wave function is because, well, we don't know what A is, we don't know what B is, and we don't know what K is either. We know K in terms of the mass of the particle that we're concerned with, Planck's constant, and the E, separation constant, we got from deriving the time-independent Schrödinger equation. While that might be related to the energy, we don't know anything about these things. These are free parameters still. But we haven't used everything we know about the situation yet. In particular, we haven't used the boundary conditions. And one thing the boundary conditions here will determine is the form of our solution. Now, what do I mean by boundary conditions? Well, the boundary conditions are what you get from considering the actual domain of your solution and what you know about it, in particular at the edges. Now, we have a wave function that can only be non-zero between 0 and a. Outside that, it has to be 0. So we know right away our wave function is 0 here and 0 here. So whatever we get for those unknown constants, a, b, and k, it has to somehow obey this. We know a couple of things about the general form of the wave function. In particular, just from consideration of things like the Hamiltonian operator or the momentum operator, we know that the wave function itself, psi, must be continuous. We can't have wave functions that look like this. And the reason for that is this discontinuity here would do very strange things to any sort of physical operator that you could think of. For example, the momentum operator is defined as minus I h bar partial derivative with respect to x. The derivative with respect to x here would blow up and we would get a very strange value for the momentum. That can cause problems. By sort of contradiction then, the wave function itself must be continuous. We'll come back to talking about the boundary conditions on the wave function later on in this chapter, but for now, all we need to know is that the wave function is continuous. What that means is that since we're 0 here, we must go through 0 there, and we must go through 0 there, since we're 0 here. So, what that means, wrong color, means psi of 0 is equal to 0, and psi of a is equal to 0. What does that mean for our hypothetical solution, psi of x equals a sine kx plus b cosine kx? Well, first of all, consider this one. The wave function at 0 equals 0. When I plug 0 into this, the sine of 0, k times 0 is going to be 0. The sine of 0 is 0, but the cosine of 0 is 1. So what I'll get if I plug in 0 for psi is 1 times b. So I'll get b. Now if I'm going to get 0 here, that means b must be equal to 0. So we have no cosine solutions. No cosine part to our solutions. So everything here is going to start like sines. It's going to start going up like that. That's not the whole story, though, because we also have to go through 0 when we go through a. So if I plug a into this, what I'm left with is psi of A is equal to capital A times the sine of Ka. If this is going to be equal to 0, then I know something about Ka. In particular, the sine function goes through 0 for particular values of particular values of its argument. Sine of x is 0 for x equals integer multiples of pi. What that actually looks like on our plot here is things like this. Our wave functions are going to end up looking like this. So let me spell that out in a little more detail. Our psi of A wave function is A times the sine of K times A. And if this is going to be equal to 0, Ka has to be either 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc. This is just coming from all of the places where the sine of something crosses 0, crosses the axis. Now it turns out this is not interesting. This means psi is 0 everywhere, since the sine of 0 is, well, sine K times A. If Ka is going to be 0, then everything. If Ka is 0, K is 0. So the sine of K times x is going to be 0 everywhere. So that's not interesting. This is not a wave function that we can work with. Another fact here is that these plus or minuses, the sine of minus x is equal to minus the sine of x. Sine is an odd function. Since what we're looking at here has a normalization constant out front, we don't necessarily care whether there's a plus or a minus sign coming from the sine itself. We can absorb that into the normalization constant. So, essentially what we're working with then is that Ka equals pi, 2 pi, 3 pi, etc., which I'll just write as n times pi. Now, if K times A is going to equal n times pi, we can figure out what, well, let's just substitute in for K, which we had a few slides ago was root 2m capital E over h bar. So that's K. K times A is equal to n pi. This is interesting. We now have integers coming from n here as part of our solution. So we're no longer completely free. We in fact have a discrete set of values. Now A, that's a property of the system. We're not going to solve for that. M, that's a property of the system. H bar, that's a physical constant. The only thing we can really solve for here is E. So let's figure out what that tells us about E. And if you solve this for E, you end up with n squared pi squared h bar squared over 2m a squared. This is a discrete set of allowed energies. And I'm going to put an exclamation point there because this is important. This is the quantum part of quantum mechanics. We started with a system that by all respects was continuous and had nothing really discrete about it. And what we ended up with in the end was a discrete set of allowed energies, a discrete set of solutions. Our wave functions look like psi sub n now. We don't have just any possible value, and they're going to be big A, a normalization constant, times the sine of, and if you substitute all of this back in, Ka is n pi. What we end up with is n pi over A times x inside our sine function. This is our wave function. The spatial part, our solution to the time-independent Schrödinger equation. There's only a discrete set of them, and that's interesting. That is the quantum in quantum mechanics. One more detail to nail down here is the normalization. We know the integral from minus infinity to infinity of psi star psi dx has to equal 1, well, in this case, we know that's going to reduce to the integral from 0 to a of psi star psi, where I should write it here, psi n equals a times the sine of n pi over lowercase a x. So I can write down psi star psi now, and that's going to give me a squared sine squared n pi over a times x, integrating dx. There's no real reason for complex conjugates here, since this is a purely real function. So the integral just ends up looking like this. And this has to equal 1 if the wave function is going to be treated as a probability distribution. Now, integrating sine squared over an interval like this, you need to be a bit careful that the interval you're integrating over has a certain minimum number of cycles. In this case, it has an even number of cycles. Not an even number. It has a specific integer number of cycles. And if you're integrating over an integer number of cycles of sine squared effectively averages out to a half. If you want to do the integral here more rigorously, you can make the substitution that sine squared of x is a half minus a half cosine of 2x. And the integral of cosine you can do. But for now, I'm just going to simplify this and say this averages out, the sine squared part here averages out to a half. And what we end up with then is a squared times a half of the actual interval we're integrating over, 0 to a. So technically this should be a minus 0, but you get the idea. The integral must equal 1 in order for things to be normalized, which tells us that a is equal to the square root of 2 over a. Big A is the square root of 2 over little a. So that determines our normalization constant. Now we know everything about our solutions. Psi sub n of x is root 2 over a times the sine of n pi over a x. That's our wave function, normalized and ready for use. So, these are our solutions, and these are the energies associated with those solutions, and we only got a discrete set of them. In order to better visualize this, I'm going to draw a diagram for you, and this is a common sort of diagram to draw in quantum mechanics, though it does abuse the system of units a little bit. If this is our x-axis, we know our wave function is only non-zero, in between 0 and a. So we have this region that we're interested in. Now I want you to think about this y-axis now as a hybrid energy wave function axis. Now treating it as an energy axis, I'm going to make some marks here. Yeah, maybe I can go up to 16 there. And each of these marks represents sort of one unit of energy. I'll label this lowestmost tick mark E1. What I get if I substitute 1 in for n in this expression for the energy. Essentially, pi squared h bar squared over 2ma squared is this value. Now, E1, consider a line at E1. Now treat this as an axis for a plot of the wave function. Now we know what the wave function looks like for E1. If we substitute 1 in for n here as well, we just get sine pi over a times x with a normalization constant. Just to show the shape of this wave function, we don't really care about the normalization constant. And it looks something like that. Now, if I continue up to E2 here, if I substitute 2 in for this, means I'm going to be getting a 4 here, so it's 4 times bigger than E1. So I go up to 4 for E2, and I draw a second line across. Now I can plot the wave function psi2. We're going to have a 2 here, so we're going to effectively go from 0 to 2 pi as x goes from 0 to a. So what that means is going to look like It's a full cycle. I'm not doing a very good job drawing it. Full cycle of a sine wave. I can keep going now. If I substituted 3 in here, I would get 9 times what I get if I substitute 1 in here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We're up to here. 5, 6, 7, 8, 9 here. It's going to be E3. And I can draw a line across here. Consider that now as the x-axis for the wave function psi 3. And that's going to be 3 half cycles of a sine wave. And you can continue on. If I go up to, say, 4, E4 is going to be at 16 times E1. It's going to be somewhere up here. It's going to look something like that. So, half a cycle, 2 half cycles, 3 half cycles, 4 half cycles, gradually moving up in energy from effectively 1 to 4 to 9 to 16, going up as n squared. So this is what our wave functions look like, and they have a lot of nice properties that we'll talk about later. But just to highlight one, if you look at the middle of the interval here, a over 2, either the wave function has a maximum or it has a 0. Maximum, 0. And the trend continues. Maximum 0, maximum 0, maximum 0, maximum 0, as you continue to go up in energy. If you center yourself at the midpoint of this interval, your wave function is either even or odd, and it's alternatingly even and odd. Even about the midpoint, odd about the midpoint. Even about the midpoint, odd about the midpoint. And this sort of general structure and the degree of symmetry we have here leads to some really nice mathematical properties that connect this analysis with Fourier analysis, Fourier series in particular, which is what we'll talk about next. For now, to check your understanding, here are 2 arguments about what we did over the last couple of slides that disagree with what we did, and your job is to figure out what's wrong with these arguments. I keep talking about solutions to the time-independent Schrödinger equation and how they have nice mathematical properties. What that actually means is, well, what I'm referring to are the orthogonality and completeness of solutions to the time-independent Schrödinger equation. What that actually means is the topic of this lecture. To recap, first of all, these are what our stationary states look like for the infinite square well potential. This is the potential such that v of x is infinity if x is less than 0 or x is greater than a, and 0 for x in between 0 and a. So if this is our potential, you express the time-independent Schrödinger equation, you solve it, you get sine functions for your solutions. You properly apply the boundary conditions, mainly that psi has to go to 0 at the ends of the interval because the potential goes to infinity there. And you get n pi over a times x as your argument to the sine functions. And you normalize them properly, you get a square root of 2 over a out front. The energies associated with these wave functions, and this energy now is the separation constant in the conversion from the time-dependent Schrödinger equation to the time-independent Schrödinger equation, are proportional to n, that index. The wave functions themselves look like sine functions, and they have an integer number of half wavelengths, or half cycles, in between 0 and a. So this orange curve, this is n equals 1. The blue curve is n equals 2. The purple curve is n equals 3. And the green curve is n equals 4. If you calculate the squared magnitude of the wave functions, they look like this. 1 hump for n equals 1. 2 humps for the blue curve, n equals 2. 3 humps for the purple curve, n equals 3. And 4 humps for the green curve, n equals 4. So you can see just by looking at these wave functions that there's a lot of symmetry. One thing we talked about in class is that these wave functions are either even or odd about the middle of the box, and this is a consequence of the potential being an even function about the middle of the box. If I draw a coordinate system here, going between 0 and a, either the wave functions have a maximum or they have a 0 at the middle of the box. So for n equals 1 we have a maximum, for n equals 2 we have a 0. And this pattern continues. The number of nodes is another property that we can think about. And this is the number of points where the wave function goes to 0. For instance, the blue curve here for n equals 2 has 1 node. This trend continues as well if I have a wave function that, for instance, let me draw it in some absurd color, has 1, 2, 3, 4, 5, 6, 7 nodes. You know this would be for n equals 8. This would be sort of like the wave function for n equals 8. These symmetry properties are nice. They help you understand what the wave function looks like, but they don't really help you calculate. What helps you calculate are the orthogonality and completeness of these wave functions. So what does it mean for two functions to be orthogonal? Let's reason at this from a perspective which you're more familiar, the orthogonality of vectors. We say two vectors are orthogonal if they're at 90 degrees to each other, for instance. So if I had a two-dimensional coordinate system, and one vector pointing in this direction, let's call that A, and another vector pointing in this direction, let's call that B, I would say those two vectors are orthogonal if they have a 90-degree angle separating them. Now that's all well and good in 2 dimensions. It gets a little harder to visualize in 3 dimensions, and, well, what does it mean for two vectors to be separated by 90 degrees if you're talking about a 17-dimensional space? In higher dimensions like that, it's more convenient to define orthogonality in terms of the dot product. And we say two vectors are orthogonal in that case if the dot product of those two vectors is 0. Now in 2 dimensions, you know the dot product is given by the x components of both vectors, ax times bx, plus the y component of those two vectors multiplied together, ay times by. If this is 0, we say these two vectors are orthogonal. In 3 dimensions, we can say plus az times bz. And if this is equal to 0, we say the vectors are orthogonal. And you can continue this multiplying together like components, or same dimension of the components of the vectors in each dimension, multiplying them together. a1, b1, a2, b2, a3, b3, a4, b4, all added up together. And if this number is 0, we say the vectors are orthogonal. We can extend this notion to functions. But what does it mean to multiply two functions like this? In the case of vectors, we were multiplying like components, both x components, both y components, both z components. In the case of functions, we can multiply both functions' values at particular x coordinates and add all those up. And what that ends up looking like is an integral. Say the integral of f of x, g of x, dx. So I'm scanning over all values of x instead of scanning over all dimensions, and I'm multiplying the function values at each individual point, at each individual x, together, and adding them all up, instead of multiplying the components of each vector together at each individual dimension and adding them all up. The overall concept is the same, and you can think about this as, in some sense, a dot product of two functions. Now in quantum mechanics, since we're working with complex functions, it turns out that we need to put a complex conjugate here on f in order for things to make sense. This should start to look familiar now. You've seen expressions like the integral of psi star of x times psi of x dx is equal to 1, our normalization condition. This is essentially the dot product of psi with itself. Psi, of course, is not orthogonal to itself, but it is possible to make a pair of functions that are orthogonal. And we say functions are orthogonal if if and only if the integral over the domain of the functions now, which I'm leaving off, there are limits on this integral, but I'm leaving them off, f star of x, g of x, dx is equal to 0. As a brief side note here, we can also make a connection with the magnitude of a vector, or the norm. For instance, we say if a vector dot a vector is equal to 1, we call this a unit vector. And in the case of functions like this, if, for instance, the integral of psi star psi dx is equal to 1, then we say psi is normalized. So both of these concepts, like dot products and unit vectors, dot products and normalized functions, or inner products of functions, you may hear that term as well, can be generalized. Orthogonality turns out to be really useful because integrals like this appear a lot in quantum mechanics, and it's very handy when we can look at an integral and say, oh, it's 0. In the case of the particle in a box, or the infinite square well potential, we got sine functions. So what does this actually look like in real life? Well, sine functions obey an orthogonality condition, and this is the orthogonality integral. Now I'm just going between 0 and a, and I have the sine of n pi over a times x, sine of m pi over a times x. And right now I'm going to stipulate that m is not equal to m. m is not equal to n. You'll see where this comes in later. This integral can be done reasonably easily if you remember your trig identities. And I certainly don't remember my trig identities. I have to go and look them up all the time. But sine of x times sine of y, this is a product identity for sine, is equal to 1/2 of cosine x minus y minus the cosine of x plus y. If you apply this identity to this product, what you end up with is a half out front, the integral from 0 to a, as before, and now we have two cosine terms. And we're going to have a cosine of n minus m pi x over a plus cosine of n plus m pi x over a, all integrated dx. This is now an integral you can do. It's just an integral of cosine. And what you get, if n is not equal to m, this term is non-zero, this term is non-zero. Both of these just work out fine. And we end up with, for our integral, where did it go? A half out front, as before, a over n minus m pi times the sine of n minus m pi x over a plus, is there a plus? Sorry, I've gotten the sign backwards here. This sign should be minus, same as this sign. The sign should be minus here as well. A over n plus m pi sine n plus m pi x over a. And this whole thing is evaluated between 0 and a. Now, I can do the evaluations. If I plug in a for this, I'm going to be plugging in an a here for this x. So the a's are going to cancel, and I'm just going to be left with n minus m pi. This is going to be a half, ugly half, going to be a half of, actually let's pull the a out front, since I have an a here and an a here. Let's pull the pi out front as well. So I've got a over 2 pi out front, and then I'm going to have sine of n minus m pi over n minus m minus the sine of n plus m pi over n plus m. This is it evaluated at a, and if I evaluate it at 0, well, I get 0. Because if I substitute 0 in for x here or 0 in for x here, the whole argument of sine is 0, and sine of 0 is 0. So this is our answer. But we know that sine of n and m both being integers, the sine of an integer times pi is also 0. So these are 0 as well. The sine term here goes to 0, the sine term here goes to 0. And what we're left with is just 0. Which means, subject to our assumption that m is not equal to m, the sine of n and m, these two sine functions of n pi x over a and n m pi x over a, are orthogonal. In the case of normalized wave functions, these constants out here end up canceling out, and what you end up with is the integral of psi star psi, I'll write out the dependence, the integral of psi sub n star of x and psi sub m star of x integral dx. Now the integral is from 0 to a, is equal to, I'm going to write this in terms of something called the Schrödinger delta, delta mn, where delta mn is defined to be 1 if m equals n, and 0 if m is not equal to n. So these are the sort of orthogonality conditions we'll be working with in quantum mechanics, and writing them out in terms of the Schrödinger delta is a handy way of doing things. That's what orthogonality actually looks like for the solutions to the time-independent Schrödinger equation for the infinite square well potential, the particle in a box. If I move forwards a little bit, where are we going with this? These orthogonality conditions are really handy, thanks to something called Fourier's trick, what your textbook, what Griffiths calls Fourier's trick. And the trick goes like this. Suppose I have some general function of x. I'm going to hypothetically say I'm going to write this function, f of x, as an infinite sum of constants multiplied by sine functions. If this were possible, how would I find the Cn, C sub n, necessary to write this? And it turns out that you can do this pretty easily. What you do is take f of x, which is equal to the sum over n equals 1 to infinity of C sub n sine n pi x over a, and from the left I'm going to integrate both equations, but before I integrate them I'm going to multiply them by sine m pi x over a, sine m pi x over a. And these are both integrals dx, which I can make some space for. So I'm taking this original equation and I'm multiplying it from the left by sine m pi x over a, and I'm integrating from 0 to a dx, both sides of this equation. If I do this, there's not much I can do with the left side since I don't know what f of x is, but I can work with the right-hand side. So let's look at the right-hand side here. The right-hand side, first thing I'm going to do is I'm going to exchange the order of summation and integration, and I'm going to pull the constant c sub n out of the integral. So what I have on the far left then is the sum from n equals 1 to infinity, c sub n times the integral of from 0 to a of sine m pi x over a times this sine n pi x over a dx. Now, you know what this integral looks like. This looks like the orthogonality condition we were working with on the last page. So it turns out this is going to be equal to 0 if n is not equal to m. So if you imagine this sum as being this term repeated over and over and over again for different values of n, all of those terms are going to vanish except for the one term when n equals m. So what that means is that we no longer have a sum here, we have only a single term, and that single term is given by Cm, integral from 0 to a, of sine of m pi x over a times the sine of m pi x over a, since n is now equal to m. So I'm just going to write this as sine squared dx. And this looks like our normalization condition. We know how to do this integral. This just comes out to a over 2. So we've done all of our integrals and we've made our sum go away, which is a pretty neat trick. We have our left-hand side over here, and our right-hand side is just cm times a over 2. So we can solve for cm, and what you get is that cm is equal to 2 over a times the integral from 0 to a of f of x sine m pi x over a dx. This tells us that if this is possible, to write f of x as a sum like this, it gives us a formula for what numbers to use in the sum. So that's all well and good. But does that actually work? This is nice because it allows us, or it hypothetically allows us to express any function. In the context of the Schrodinger equation, this would be any initial conditions to the Schrodinger equation. And it allows us to express that as a sum of, these are now going to be our stationary states. So our initial conditions maybe we can express them as a sum of stationary states. You know, superpositions of stationary states are also solutions to the Schrodinger equation. So this is good. It allows us to construct whatever sort of wave function we want in terms of the functions that we have. If we follow this formula, maybe it will work. Does it work? That's the other property that's really nice about solutions to the time-independent Schrodinger equation. They form what's called a complete basis. They are a complete basis set. This is like having a set of unit vectors with which you can express any other unit vector. For instance, x hat, y hat, and z hat. Unit vectors pointing in the x, y, and z directions form a basis for 3D space. If we have a set of solutions to the Schrodinger equation, for instance, the solutions to the Schrodinger equation for the infinite square well potential, our sine function, they actually form a complete basis for functions. Which means this formula for expressing some function f of x in terms of a sum of sine functions, where the numbers used in the sum are calculated by this Fourier's trick sort of integral, this actually works for damn near any f of x. Not quite any, just for the sake of being mathematically rigorous. This is really only going to work for smooth square integrable functions. Eesh. If f of x blows up to infinity, this isn't going to work. And if f of x has a lot of corners and discontinuities, this isn't going to work either. But for smooth square integrable functions, which happens to be what we really care about for quantum mechanics, this works. How does this actually work out? Why does this actually work out? Just to say very briefly, conceptually, how this works. This works because it is possible to write sum of c sub n sine of n pi x over a, such that if I plotted this as a function of x between 0 and a, I can make functions that look like this. I can make functions that are very sharp and very tall. And I can make these functions wherever I want by suitable choices of this Cn. So if I change Cn, I can change the position of this spike. And I can make this spike as sharp as I want, and I can make it as tall or as short as I want. And what that means is I can make whatever function you want. For instance, suppose the function you want looks something like this. I can make it by adding up a bunch of spikes. I can have a little spike here, and a little spike here, and a little spike here, a little spike here, etc. If I effectively fill this whole space with these very sharp spikes going up to the value of the function, I can recreate whatever function you want, no matter what shape it is. Provided it's reasonably well behaved and square integrable, this actually works really well. What this looks like graphically is shown here. This is some hypothetical f of x. F of x is shown in black now, and it runs from down here to up here. It's just a straight line. Now, if I only include the first term in this long sum. Remember, now we're expressing f of x as the sum of n equals 1 to infinity of c sub n times sine of n pi x over a. If I only let the sum go from n equals 1 to 1, I get the blue curve here. So there's only one term in this sum, you just get a sinusoid. It's not a very good approximation to the straight black curve. But if I let n become larger, in this case I think I have n equals 20 here for the purple curve, you can see the purple curve drops very rapidly, wiggles, but is mostly going straight along the black curve. It's having some difficulty matching the black curve at the endpoints here, and that's because part of this assumption here that we're working with sine functions, these are from the solutions to the Schrödinger equation, not from a rigorous treatment of Fourier series or Fourier expansions of functions. So since we're requiring our purple curve here to go through 0, of course it's going to have to give up on fitting the function near the endpoints. But if you include a lot of terms in this, you can make this approximation quite good. Generally, the more terms you add, the closer you get to your function. So, to sum up, the solutions to the time-independent Schrödinger equation for the particle in a box are these sine functions, and these sine functions obey an orthogonality condition. And that orthogonality condition allows you to find out relatively easily what constants to use in an expression of any function as a sum of sine functions, as a sum of stationary states. So if we have some initial conditions for our wave function, we can express it as a sum of stationary states. We then know the way stationary states evolve with time. We know then everything about how our wave function will evolve forwards in time. To check your understanding, here are two relatively straightforward problems to use Fourier's trick and the orthogonality conditions for sine to determine, for instance, C2, C3, and C4 for this f of x, or C2 for this f of x. So, we've been working with solutions to the time-independent Schrödinger equation for the infinite square well potential, the particle in a box case. How do these things actually work, though? In order to give you guys a better feel for what the solutions actually look like and how they behave, I'd like to do some examples and use a simulation tool to show you what the time evolution of the Schrödinger equation in this potential actually looks like. So, the general procedure that we've followed or will be following in this lecture is, once we've solved the time-independent Schrödinger equation, we get the form of the stationary states. Knowing the boundary conditions, we get the actual stationary states, the stationary state wave functions and their energies. These can then be normalized to get true stationary state wave functions that we can actually use. These stationary state wave functions will, for the most part, form an orthonormal set, psi sub n of x. We can add the time part, knowing the time-dependent Schrödinger equation, or the time part that we got when we separated variables in the time-dependent Schrödinger equation. We can then express our initial conditions as a sum of these stationary state wave functions and use this sum then to determine the behavior of the system. So what does that actually look like in the real world? Not like very much, unfortunately, because the infinite square well potential is not very realistic, but a lot of the features that we'll see in this sort of potential will appear in more realistic potentials as well. So, this is our example. These are our stationary state wave functions. This is what we got from the solution to the time-independent Schrödinger equation. This was the form of the stationary states, these were the energies, and then this was the normalized solution with the time dependence added back on, since the time dependence is basically trivial. The initial conditions that I'd like to consider in this lecture are the wave function evaluated at 0 is either 0 if you're outside the, this should be A. If you're outside the domain, you're 0. If you're inside the domain, you have this properly normalized wave function. We have an absolute value in this, which means this is a little difficult to work with. But what the plot actually looks like if I draw a coordinate system here, going from 0 to a, is this. It's just a tent, a properly built tent with straight walls going up to a nice peak in the middle. Our general procedure suggests that we express this initial condition in terms of these stationary states with their time dependence, and that will tell us everything we need to know. One thing that will make this a little easier to work with is getting rid of the absolute values we have here. So let's express psi of x time t equals 0 as a three-part function. First, we have root 3 over a, 1 minus. Now what we should substitute in here is what we get if, say, 0 is less than x is less than a over 2. Sort of the first half interval going out to a over 2 here. In this case, we have something sloping upwards, which is going to end up, in this context, being 1 minus a over 2 minus x over a over 2. So, to say another word or two about that, if x is less than a over 2, this quantity here will be negative. So I can get rid of the absolute value if I know that this quantity in the numerator is positive. So I multiply the quantity in the numerator by a minus sign, which I can express more easily just by writing it as a over 2 minus x. a over 2 minus x. That will then ensure that this term here is positive for x's in this range. 1 minus that is then this term in our wave function. For the other half of the range, root 3 over a, 1 minus something, and this is now from a over 2 is less than x is less than a, the second half of the interval. For the second half of the interval, x is larger than a over 2, so x minus a over 2 is positive. So I can take care of this absolute value just by leaving it as x minus a over 2. I don't need to worry about the absolute value in this range. So this is x minus a over 2 all over a over 2. And of course, if we're outside that, we get 0. This technique of splitting up absolute values into separate ranges makes the integrals a little easier to express and a little easier to think about. So that is our initial conditions. How can we express these initial conditions as a sum of stationary state wave functions evaluated at time t equals 0? This is where Fourier's trick comes in. If I want to express my initial conditions as a sum of stationary state wave functions, I know I can use this sort of an expression. This is now my initial conditions, and my stationary state wave functions are being left multiplied, complex conjugated, integrated over the domain, and that gives us our constants, c sub n, that go in this expression for the initial conditions in terms of the stationary state wave functions. The notation here is that if psi appears without a subscript, that's our initial condition, that's our actual wave function, and if psi appears with a subscript, it's a stationary state wave function. So what does this actually look like? Well, we know what these functions are. First of all, we know that this function, which has an absolute value in it, is best expressed if we split it up in two. So we're going to split this integral up into one going from 0 to a over 2 and one going from 0 to a. So let's do that. We have c sub n equals the integral from 0 to a over 2 of our normalized stationary state wave function, which is root 2 over a times the sine of n pi x over a. That's this psi sub n star, evaluated at time t equals 0. I'm ignoring time for now, so even if I had my time parts in there, I would be evaluating e to the 0, where time is 0. So I would get 1 from those parts. Then you have psi, our initial conditions, and our initial conditions for the first half of our interval was root 3 over a, 1 minus a over 2 minus x over a over 2. And I'm integrating that dx. The second half of my integral from a over 2 to a, looks much the same. Root 2 over a sine n pi x over a. That part doesn't change. The only part that changes is the fact that we're dealing with the second half of the interval, so the absolute value gives me a minus sign up here more or less. Root 3 over a, 1 minus x minus a over 2 over a over 2 dx. So, substitute in for n and do the integrals. This, as you can imagine, is kind of a pain in the butt. So what I'd like to do at this point is give you a demonstration of one way that you can do these integrals without really having to think all that hard. And that's doing them on the computer. You can of course use Wolfram Alpha to do these. You can of course use Mathematica. But the tool that I would like to demonstrate is called Sage. Sage is different than Wolfram Alpha and Mathematica in that Sage is entirely open source and it's entirely freely available. You can download a copy, install it on your computer, and work with it whenever you want. It's a very powerful piece of software. Unfortunately, it's not as good as the commercial alternatives, of course, but it can potentially save you a couple $100. The interface to this software that I'm using is their notebook webpage. So you can use your Google account to log into this notebook page, and then you have access to this sort of an interface. So, if I scroll down a little bit here, I'm going to start defining the problem. A, here, that's our domain. Our domain goes from 0 to a. H bar I'm defining to be equal to 1, since that number is a whole lot more convenient than 10 to the minus 31st. N, x, and t, those are just variables, and I'm defining them as variables given by these strings, n, x, and t. Now we get into the physics. The energy, that's a function of what index you have, what your which particular stationary state you're talking about. This would be psi sub n. This would be E sub n. E sub n is equal to n squared pi squared h bar squared over 2ma squared. That's an equation that we've derived. Psi of x and t, psi sub n of x and t in particular, is given by this. It's square root of 2 over a times this sine function times this complex exponential, which now uses the energy, which I just defined here. Psi star is the complex conjugate of psi, which I've just done by hand by removing the minus sign here. More or less just a copy-paste. G of x is what I've defined the initial conditions to be, which is square root of 3 over a times this 1 minus absolute value expression. And C sub n here, that's the integral of g of x times psi from 0 to a over 2 plus g of x times psi going from a over 2 to a. That's all well and good. Now I've left off the psi stars, but since I'm evaluating at time t equals 0, it doesn't matter. Psi is equal to psi star at t equals 0. I did have to split up the integral from 0 to a over 2 and a over 2 to a, because otherwise Sage got a little too complicated in terms of what it thought the integral should be. But given all this, I can plot, for instance, g, and if I click evaluate here, momentarily a plot appears. This is the plot of g of x as a function of x. Now I defined a to be equal to 1, so we're just going from 0 to 1. This is that tent function I mentioned. If I scroll down a little bit, we can evaluate c of n. This is what you would get if you plugged into that integral that I just wrote on the last slide. You can make a list evaluating c of n for x going from 1 to 10, and this is what you get. You get these sorts of expressions. 4 times square root of 6 over pi squared, or minus 4 root 6 over pi squared divided by 9, 4 root 6 over pi squared over 25, 4 root 6 over pi squared over 49. You can see the sort of pattern that we're working with. Some number divided by an odd number raised to the nth power, or squared. We can approximate these things just to get a feel for what the numbers are actually like. And we have 0.99 minus 0.11 plus 0.039, etc. Moving on down. So that's the sort of thing that we can do relatively easily with Sage. Get these types of integral expressions and their values. You can see I've done more with this Sage notebook, and we'll come back to it in a moment. But for now, these are the sorts of expressions that you get for c sub n. So our demo with Sage tells us C sub n equals some messy expression. And it can evaluate that messy expression and tell us what we need to know. Now, the actual form of the evaluated C sub n was not actually all that complicated. And if we truncate our sum, instead of summing from, now this is expressing psi of x t, our wave function, as an infinite sum, n equals 1 to infinity, of C sub n psi sub n of x and t. If I truncate this sum at, say, n equals 3, I'll just have a term from psi 1 and psi 3. Recall back from the Sage results that psi 2, the coefficient of psi 2, C sub 2, was equal to 0. So let's find the expectation of x squared. Knowing the form of these functions and now knowing the values of these C sub n from Sage, you can write out what x squared should be. This is the expected value of x squared, and it's going to be an integral of these numbers, 4 root 6 over pi squared times psi 1, which was root 2 over a sine, not n, since we're just dealing with psi 1 now, we have pi x over a. We have to include the time dependence now, since I'm looking for the expected value of x squared as a function of time now. And we have e to the, where'd it go, minus I times pi squared h bar squared t over 2ma squared, all divided by h bar, or I could just cancel out one of the h bars here. That's our first term, in our first term of our expression. The next term, we have 4 root 6 over 9 pi squared from this coefficient. Now psi 3 is root 2 over a sine of 3 pi x over a times, again, complex exponential, e to the minus I pi squared h bar squared t over 9 pi squared h bar squared t over 2ma squared, all divided by h bar. Now, what is this? This whole thing needs to be complex conjugated, because this is psi star. What's next? Well, I need to multiply this by x squared, and I need to multiply that by the same sort of thing, e to the plus this minus same sort of thing, e to the plus this. So this is the term in orange brackets here is psi star. This is our x. The term in blue brackets here is our psi. So we're just using the same sort of expression, only you can only see just how messy it is. This is the integral of psi star x squared psi. This is psi star, this is x squared, and this stuff is psi. We have to integrate all of this dx from 0 to a. This is pretty messy as well. Messy, but doable. Now, since I was working with Sage anyway, I thought, let's see how the time dependence in this expression plays out in Sage. So, going back to Sage, we know these C sub n's, these are the C sub n's that I chose for C sub 1 and C sub 3. And C sub n of x gives me some digits. Or, sorry, C sub n evaluated gave me these numbers in just in decimal form. Now I can use these C sub n's to express that test function where I truncated my sum at psi sub 3. So this is our test function. And if you evaluate it, it's a lot more simple when you plug in the numbers, sine 3 pi x and sine pi x. When h bar is 1 and a is 1, these expressions are a lot easier to work with, which gives you a feeling for why quantum mechanics often we assign h bar equal to 1. The expected value of x squared here is then the integral of the conjugate of my test function times x squared times my test function, integrated from 0 to a. And Sage can do that integral. It just gives you this. Sage can also plot what you get as a result. Now you notice Sage has left complex exponentials in here. If you take this expression and manually simplify it, you can turn this into something with just a cosine. There is no complex part to this expression. But Sage isn't smart enough to do that numerically, so I have to take the absolute value of this expression to make the complex parts, the tiny, tiny complex parts, go away. And if I plot it over some reasonable range, this is what it looks like. It's a sinusoid, or a cosinusoid actually. And what we're looking at here on the y-axis is the expected value of x squared. This is related to the variance in x. So it's a measure of more or less the uncertainty in position. So our uncertainty in position is oscillating with time. What does this actually look like in the context of the wave function? Well, the wave function itself is going to be a sum, c sub 1 times psi 1, c sub 3 times psi 3, c sub 5 times psi 5, c sub 7 times psi 7, etc. I can do that in general by making this definition of a function, where I just add up all of the c sub n's and all the psi sub n's for n in some range. F of x, if I go out to 7, looks like this. You can get a feel for what it would look like if I added more terms as well. Now the plot that I'm showing you here is a combination of 4 things. First, it's the initial conditions shown in red. That's the curve that's underneath here, the tent. And I'm also showing you this approximate wave function when I truncate the sum at 2, just the first term. That's this poor approximation here, smooth curve. The function, if I truncate the approximation at 4, that will include psi 1 and psi 3. That's this slightly better approximation here, this one. And if I continue all the way up to 20, that's this quite good approximation, the blue curve here, that comes almost all the way up to the peak of the tent. So that's what our approximate wave functions look like, but these are all evaluated at t equals 0. What does that look like, for instance, in terms of the probability density and as a function of time? So let's define the probability density, rho of xt, as the absolute value of our approximate function, and I'll carry the approximation all the way to n equals 20, absolute value squared. And I'm getting the approximate form with this dot n at the end. So this is our approximate form of the probability density calculated with the first 20 stationary state wave functions. This plot then shows you what that time dependence looks like. I'm plotting the probability density at time t equals 0, probability density at time t 0.04, 0.08, 0.12, 0.16. We start with blue, dark blue. That's this sort of peaked curve, which should be more or less what you expect, because we did a problem like this for this sort of wave function in class. Then you go to dark green, which is under here, underneath the yellow. It seems to have lost the peak, and it's spread out slightly. Red is at time 0.08, and if I scroll back up to our uncertainty as a function of time plot, 0.08 is here. So it's pretty close to the maximum uncertainty. You expect the uncertainty, the width, to start decreasing thereafter. If I scroll back down here, this red curve then is more or less as wide as this distribution will ever get. And if we continue on in time, now going to 0.12, that was the orange curve here. And the orange curve is back on top of the green curve. The wave function has effectively gotten narrower again. And if you keep going all the way up to 0.16, you get the cyan curve, the light blue curve, which is more or less back on top of the dark blue curve. So the wave function sort of spilled outwards and then sloshed back inwards. You can sort of imagine this as ripples in a tank of water radiating out and then coming back to the center. This is what the time evolution would look like as calculated in SAGE. You can make definitions of functions like this, you can evaluate them, you can plot them, and you can do all of that relatively easily. Now I'll give you all a handout of this worksheet so that you get a feel for the syntax. If you're interested in learning more about SAGE, please ask me some questions. I think SAGE is a great tool, and I think it has a promising future, especially in education like this. For students, the fact that this is free is a big deal. So that's what the time variability looks like. We had our wave function, which started out sort of sharply peaked, our probability density, excuse me, rho of x, which I should actually write as rho of x and t, which sort of got wider and then sloshed back in. So we sort of had this outwards motion followed by inwards motion, where our expectation of x squared related to our uncertainty oscillated. Oh, sorry. It didn't oscillate about x equals 0. It oscillated about some larger value. Or sorry, it didn't oscillate about 0. It oscillated about some larger value. So there's some sort of mean uncertainty here. Sometimes you have less uncertainty, sometimes you have more uncertainty. That's the sort of time dependence you get from quantum mechanical systems. To get an even better feel for what the time variability looks like, there's a simulation that I'd like to show you. And this comes from Falstad.com, which, as far as I can tell, is a guy who was sick of not being able to visualize these things, so he wrote a lot of software to help him visualize them. So here's the simulation, and I've simplified the display a little bit to make things easier to understand. These circles on the bottom here, each circle represents a stationary state wave function. And he has gone all the way up to stationary state wave functions that oscillate very rapidly, in this case. But this is our ground state. This is our first excited state, second excited state, third excited state, etc. N equals 1, 2, 3, 4, 5, 6, 7, etc. Now, in each of these circles, there may or may not be a line. The length of the line represents the magnitude of the time part of the evolution of that particular stationary state. And the angle going around the circle here represents the phase as that evolution proceeds. So if I unstop this simulation, you can see this slowly rotating around. You're also probably noticing the color here changing. The color of this represents the phase. The vertical size of this represents the probability density, and the color represents the phase. So it's a representation of where you're likely to find it, and a sort of color-based representation of how quickly it's evolving. The vertical red line here in the center tells you what the expectation value for position is. And in this case, it's right down the middle. If I freeze the simulation and add a second wave function, this is now adding some component of the first excited state. And by moving my mice around here, I can add varying amounts, either adding none or a lot, and I can add it at various phases. I'm going to add a lot of it, an equal amount as the ground state, and I'm going to do it at the same phase. And I'm going to release and let that evolve. So you can see now the probability density is sort of sloshing to the left and sloshing back to the right. And if you look at our amplitude and phases, you can see the ground state is still rotating. The first excited state is rotating, but the first excited state is rotating 4 times faster. So when they align, you have something on the right. When they anti-align, something on the left. They're aligned, they're anti-aligned. And this sloshing back and forth is one way where we can actually get motion out of stationary states. You notice the phase is no longer constant. You have some red parts, some purple parts, and things are sort of moving around in an awkward way. The colors are hard to read, but you know now that the phase of your wave function is no longer going to be constant as a function of position. So those exponential time parts may be giving you a wave function that's purely real here and purely imaginary here, or some combination of purely real and imaginary, some general complex number. And that complex number is not simply e to the I omega t. It's e to the I omega something that's a function of position as well as time. It's complicated. I can, of course, add some more wave functions here, and you get even more complicated sorts of evolution. Our expected value of x is now bouncing around fairly erratically. Our phase is bouncing around even more erratically. But what we're looking at here is just the sum of the first 1, 2, 3, 4, 5, 6 stationary states, each evolving with the same amplitude and different phases. Now I'm going to stop the simulation and clear it now. Another thing I can do with this simulation tool is put a Gaussian into the system. So I'm going to put a Gaussian in here. So this is sort of our initial conditions, and the simulation has automatically figured out, well, I want this much, I want a lot of the first of the ground state, psi 1, a lot of psi 3, a lot of psi 5, a lot of psi 7, a little bit of psi 9, a little bit of psi 11, etc. And if I play this, I'll slow this down a little bit first. If I play this, you see the wave function gets wide, becomes 2, gets narrower again, and sloshes back where it started. If you watch these arrows down here, you can tell when it comes back together, the arrows are all pointing in the same direction, and when it's dispersed, the arrows are sort of pointing in opposite directions. Since our initial conditions were symmetric, there's no reason to expect the expected value to ever be non-zero, ever move away from the center of this well. But as your, say, psi 1, psi 3, psi 5, psi 7, etc., oscillate at their own rates in time, the superposition results in a relatively complicated dynamics for the overall probability density. And of course I can make some ridiculously wacky initial conditions that just sort of oscillate all over the place in a very complicated way. There are a lot of contributions to this wave function now, and no one contribution is particularly winning, but you can occasionally see little flashes of order in the wave function. I highly encourage you to play with these simulations just to get a feel for how time evolution in the Schrodinger equation works. There are a lot more than just the square well here. There's a finite well, harmonic oscillator, a pair of wells. There are lots of things to play with, so you can get a reasonably good feel with how the Schrodinger equation behaves in a variety of physical circumstances. So that's our simulation, and hopefully you have a better feel now for what solutions to the Schrodinger equation actually look like. To check your understanding, explain how these two facts are related. Time variability in quantum mechanics happens at frequencies given by differences of energies, whereas in classical physics, you can set the reference level for potential energy to whatever you want, sort of equivalent to saying, I'm measuring gravitational potential from ground level versus from the bottom of this well.
Thanks for watching. Please subscribe and don't miss out on new videos and lectures.